Hoover High School. This is AP Chemistry, Covalent and Ionic Bonds. We're in Unit 7, and we're going to focus on covalent bonds on Monday and Tuesday of this week. First, we're going to start with Lewis dot structures. So let's do a review of covalent bonds. We talked about them back in the foundations unit, and we need to review that a little bit because we're going to go a little bit deeper into covalent bonds at this time. So covalent bonds occur when two or more atoms share electrons. Covalent bonds occur primarily between nonmetals such as carbon, nitrogen, oxygen, phosphorus, hydrogen, sulfur, chlorine, and the others. Covalent bonds produce combinations of atoms called molecules. Covalent bonds are the bonds that are found in you and other living organisms. So when nonmetals bond, they pull on each other's electrons very hard because they both have high electronegativity. Since they both have high ionization energies, they don't easily give up their electrons. So it's two strong guys having a tug of war. Neither one can win and take the electrons away from the other. Consequently, the two atoms share the electrons. So let's do a quick review of how covalent bonds are formed. So the octet rule says that atoms are most energetically stable, that is, they're happy, when they can fill their valence orbital. Octet means 8. It's called octet because the elements in the second period, rows, and below need 8 electrons to fill their valence outer orbital. Oxygen has 6 electrons in its valence orbital. To be in a more energetically favorable state, oxygen would like to fill those 2 empty spaces. But how does it do that? The octet rule says that atoms are most energetically stable when they can fill their valence orbital. So octet means 8. It's called the octet rule because elements in the second period and below need 8 electrons to fill their valence orbital. I'm repeating that because it's an important concept. Be sure that you have that understood. So hydrogen's valence orbital can hold 2 electrons. So hydrogen needs 1 electron to be happy and fill its valence orbital. But how does it do that? Note that even though hydrogen's first orbital can only hold 2, not 8 electrons, it's still called the octet rule. The main idea is that an atom wants to fill its valence orbital to be happy. So each hydrogen shares its electron with oxygen. This gives oxygen a total of 8 electrons, so oxygen's happy. Oxygen shares an electron to fill the valence orbital of each hydrogen, so the hydrogens are happy. So it looks like that. They pair up, and those two pair up. And there are the shared electrons. Because hydrogen atoms fill the valence orbital of oxygen, oxygen fills the valence orbital of the 2 hydrogens, this combination creates H2O, or water. These electrons are double counted. They both belong to the hydrogen atom, and at the same time, they both belong to the oxygen atom. Similarly, these electrons are double counted. They both belong to the hydrogen atom, and at the same time, they both belong to the oxygen atom. The bonds created between nonmetals by atoms sharing electrons according to the octet rule are called covalent bonds. Think about that word. Co means together, like to cooperate, and valent means valence orbital. So it means they work, their valence orbitals are shared. Oxygen is more electronegative than hydrogen, so it pulls the electrons more strongly toward it. The water molecule below is polar. This side of the molecule contains the nuclei of 2 hydrogen atoms, that is 2 protons. The red rectangle has a charge of +2. So you see, if we can kind of sector off the water molecule, you can divide it so that you have a positive end and a negative end. So the red end has only 2 protons in it, so it has a +2 charge. This side of the molecule contains 8 protons and 10 electrons. You can count them. The 8 protons all belong to the oxygen atom, and the 10 electrons are the entire set of electrons there. The blue rectangle has a charge of 8 minus 10, or 2 minus. A polar molecule is an electrically neutral molecule that has a positive side and a negative side. This means it acts like a magnet when other polar molecules are nearby. Covalent bonds form molecules. These H2O water molecules, for example, are separate structures from all other water molecules. When water boils, the water molecules separate and move freely. Think of molecules as cars that can move independently of one another. Okay, Lewis dot structures. Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and valence electrons. So this is the way we've learned how to diagram an oxygen atom. Now to do the Lewis dot structure, you simply write the atomic symbol for oxygen, which is O, and then you draw only the valence electrons around the symbol, not those 2 first orbital electrons, but only the 6 second orbital electrons. So they would be placed like this. And the important thing about this particular structure is that it has 2 unpaired electrons. The one on the top and the one on the right are unpaired. That's where the hydrogens can come in and plug in their electrons to create a chemical bond. The Lewis dot representation of a water molecule is shown below. All atoms want to fill their valence orbitals. Oxygen agrees to share one of its unpaired electrons with a hydrogen if hydrogen shares its electron with oxygen. Oxygen repeats this process with another hydrogen atom. Both hydrogen atoms and oxygen end up with filled valence orbitals, creating a covalent bond and fulfilling the octet rule. We want to create a bond between 2 oxygen atoms. Each wants a full octet, 8 electrons, but each has only 6 electrons to contribute. So how does it do that? How can it have 2 octets in its valence orbital? That's 2 times 8 is 16. When each one only has 6, that's 2 times 6 is 12 electrons total. How can we create 2 octets from 12 electrons? That each oxygen shares both of its unpaired electrons to form what is called a double bond. Notice that each oxygen atom has 8 electrons in its valence orbital because the electrons in the yellow area are counted for both atoms. Double bonds, it should be pointed out, are shorter. They're shorter than single bonds. You may think they might be longer because they have more electrons in the middle there, but they're actually shorter and they're stronger than single bonds. The Lewis dot structure diagram for the O2 molecule looks like this. In a covalent bond, electrons that bond 2 atoms are called bonding electrons. Electrons that do not bond 2 atoms are called non-bonding electrons or lone pair electrons. A pair of bonding electrons can be represented by a line. Lines should not be used to represent lone pair electrons. Okay. Now what we're going to do is, this was all review up until now. Now what we're going to do is learn how to apply Lewis dot structures to learn how to construct a molecule, a covalently bonded molecule. And there's a series of rules. The 2 goals that you want to do when you're creating a Lewis dot structure of a covalently bonded molecule is, first, all valence electrons contributed by the bonded atoms must be placed in the molecule. You have to use all of the electrons. You can't use more than the number of valence electrons that you were given. And 2, all atoms have full octets, with limited exceptions to be discussed later. So here are the rules. They're going to sound a little confusing at first, but once you apply them a few times, they won't seem that hard. You just have to practice. Okay, so determine the total number of valence electrons. Then you draw the structure of the molecule, and how you do that we'll talk about. Here's a couple of rules. The least electronegative atom occupies the center of the molecule and is usually written first in the formula. Hydrogen and fluorine must occupy outside terminal positions. The reason for that is hydrogen can only bond in one place. Therefore, it can't be a central atom. A central atom has to be able to bond at least 2 different places, so it has 2 other atoms on either side of it. So it has to bond at least 2, maybe more places. Fluorine is the most electronegative element, so it can never be the central. If the least electronegative is supposed to go in the middle, that could never be fluorine. Then you connect the outside atoms with the central atom using single bonds. You create octets for all the terminal outside atoms. You assign the remaining electrons as lone pairs around the central atom. And you form multiple bonds with the central atom if necessary. So these are kind of like little puzzles that you're putting together, and you'll see how these rules work as we apply them. So here we're going to do a simple example. One we've already put together before is H2O. But let's do it following the rules. So determine the total number of valence electrons. So you have 2 hydrogen atoms. Each one has 1 valence electron. That's a total of 2 valence electrons. By the way, get used to the notation E minus. That means electron. And then oxygen there's 1 atom of oxygen. It has 6 valence electrons. Remember, we're only counting valence electrons, not the total number of electrons. So that means there's 6 electrons. So if you add those up, you get 8 electrons total between the 2 atoms. A water molecule has a total of 8 valence electrons. So now we're going to draw the structure. The least electronegative atom occupies the center of the molecule and is usually written first in the formula. Hydrogen and fluorine must occupy outside positions. So there's how we draw this. So we have conflicting rules here, if you notice. The least electronegative atom is hydrogen. It has an electronegativity of 2.1. That's much lower than oxygen. However, hydrogen, rule B says hydrogen cannot occupy a central atom position. It must be an outside atom. And that's simply because it can only bond on one side. So therefore, which of these rules takes precedence? In this case, B takes precedence. Hydrogen has to go on the outside. So rule 2A and 2B conflict. H is less electronegative than oxygen. However, H can bond in only one location. So H cannot be a central atom. Therefore, O is placed as the central atom. Now you connect the outside atoms with the central atom using single bonds. So there we've done that. Now we've used 4 of our 8 electrons. Remember, we had 8 electrons that we have to place. And now we've used 4 of them. So create octets for all terminal atoms. Well, hydrogen already has a full octet, 2 electrons. Hydrogen can't handle any more than 2 electrons, so it already has a full octet. So assign remaining electrons as lone pairs around the central atom, and so there we go. We put the rest of the electrons there. And form multiple bonds with the central atom if necessary, and this rule is not necessary in this example. So the 2 requirements for a covalent bond have been met. First of all valence electrons have been placed. We started off with 8 valence electrons, and in that diagram you see we've placed 8 valence electrons. And second of all atoms have full octets, and they do. Oxygen has 8, which any second row element would need, and hydrogen has 2, which any first row element would need to fill an octet. Therefore, we've completed our diagram. 2 other notes about the Lewis structure for H2O. The bonding electron pairs can be represented by a line, as shown on the right. Non-bonding lone pair electrons cannot be shown in this way. Also, number 2, H2O is not a linear straight molecule the way it's shown here. The rules for determining the geometry of molecules will be covered later. But for right now, this is good enough. You can draw it like this. Okay, now we're going to do the same thing with oxygen, O2. So first, determine the total number of valence electrons. So we have 2 oxygen atoms. Each one again has 6 valence electrons. So that's a total of 12 electrons that we're going to have to place. An oxygen molecule has a total of 12 valence electrons. So now we draw the structure. Well, that's pretty simple. The least electronegative atom appears at the center of the molecule, hydrogen and fluorine. Anyway, these rules don't apply because all you have is 2 oxygens. So they both could be considered central atoms for this. Both oxygen atoms are considered central. Okay, 3, connect the outside atoms with the central atom using single bonds. So we just have the 2 atoms, so there's a single bond between the 2 oxygens. So now we've used 2 out of the 12 electrons. Create octets for all terminal outside electrons. So we start there, and now we add that. Now they both have an octet. Reduce the number of electrons to the number computed in step 1 by eliminating lone pair electrons. Assign remaining electrons as lone pairs around the central atom. Okay, so now that's where this becomes a little bit of a puzzle. We have 12 electrons that we have to place, exactly 12, no more, no less. If you count the number of electrons there, you have 14. So 2 things have to happen. We have to get rid of 2 of those electrons. Just make them disappear. Those will be 2 of the lone pair electrons. It doesn't matter which 2 you pick. Just get rid of 2 of the electrons. But once we do that, if we get rid of any of those lone pair electrons, one of the oxygens will not have an octet. So then we have to figure out a way to rearrange another one of the lone pairs so that both atoms have an octet. So stop and think about that. You got to get rid of 2 of them, so just take 2 of them away. Doesn't matter which 2. Then figure out, if you take, let's say you take 2 of them away from the oxygen on the right, it's only going to have 6 electrons around it. It needs to have 8. So that means you have to take 2 of the others from somewhere and place them so that that oxygen on the right will have 8 electrons again. It has to do that. So the first step is we're going to do this, and we can choose which lone pair to remove. So we're going to choose that lone pair. We're going to take it away. And so now you see the oxygen on the right only has 6. So we have to place 2 of the other lone pairs, or 2 of the other electrons in lone pairs somewhere so that that oxygen on the right has 8 again. Can you figure out how to do that? It's a little bit of a puzzle. So here's what we do. Form multiple bonds with the central atom if necessary. In this case, it's necessary. Now you have to form a double bond with the oxygen. So we're going to take those 2 and we're going to stick them in the middle there. And now you have 12 electrons, and both oxygens have 8, an octet. Because remember, the 4 in the middle count for both oxygen atoms. So we met both requirements for a covalent bond. We've used all 12 of the valence electrons. We create octets around both oxygen atoms. So that's the completed structure. So oxygen O2 molecules are double bonded. Okay, let's do HCN. This is a little more interesting because there's 3 different elements involved. So we're going to determine the total number of valence electrons. So there's 1 hydrogen. It has 1 valence electron, so that's 1. 1 carbon, it has 4 valence electrons for 4. And 1 nitrogen has 5 valence electrons. So now we're going to add those up. So now we have 10 valence electrons that we have to place in our molecule. So an HCN molecule has a total of 10 valence electrons which must be placed in the molecule. So draw the structure. Okay, now you have to follow these rules. The least electronegative atom occupies the center of the molecule and is usually written first in the formula. Hydrogen and fluorine must occupy outside terminal positions. So that means hydrogen is not going to be the central molecule. It's either going to be carbon or nitrogen. So which of those 2 is least electronegative? So go to your electronegativities, periodic table of electronegativities, and you will see that carbon is just to the left of nitrogen. Remember, electronegativities get higher as you go to the right on the periodic table. Carbon is just to the left of nitrogen, so it's less electronegative than nitrogen. So there's the electronegativity for hydrogen. There's the electronegativity for carbon. There's the electronegativity for nitrogen. So hydrogen has the lowest electronegativity, but it cannot be a central atom because it only can bond in one place. This makes carbon the central atom. So this is the structure that you're going to come up with, HCN. So connect the outside atoms with the central atom using single bonds. So there we go. So right there you have 4 electrons. So you've used 4 of the 10 electrons that you need to place. Create octets for all terminal outside atoms. So there we've created an octet for nitrogen, and hydrogen cannot take any more electrons. So we have now used the 10 valence electrons. If you count them, you have 10 electrons down there. However, carbon does not have an octet. So what do we do about that? Well, think back to the oxygen example we just did. We don't need to get rid of any electrons this time because we have 10, we need to use 10, so the number of electrons is good. We just need to rearrange them. How would you do that? Think about that for a second. Pause the video. Think about how would you rearrange the electrons so that carbon has an octet and nitrogen has an octet. So rearrange the lone pair electrons to create an octet for carbon. And there it is. Create octets for all terminal outside atoms. Rearrange lone pair electrons to create the octet for carbon. So you have a triple bond between carbon and nitrogen. Triple bonds are even shorter than double bonds, and they're stronger. So shorter and stronger. Again, it may seem like they should be longer because it looks longer in that diagram, that they would have so many electrons they'd be pushing the 2 atoms apart, but they're not. They actually pull them closer together, and they're stronger than double bonds. So we've met the rules for creating a covalent bond. We've used all 10 valence electrons, and we've created octets for all elements. The 6 electrons in the triple bond are counted for both carbon and nitrogen. So carbon and nitrogen both have 8 valence electrons. Elements in group 13. Here's an exception to the octet rule. It's one of the exceptions. There's 2 others, and I'll tell you where to find those 2 others. Elements in group 13, starting with boron, are exceptions to the octet rule. Elements in group 13 compounds have only 6 valence electrons. So this is an example of BH3. Boron has 6 valence electrons in this compound, and that's complete. It can't have any more. If we did the structure for this compound, hydrogen each contributes 1 valence electron, that's a total of 3, and the boron contributes 3, that's a total of 6. So there's only 6 valence electrons to be had, and so that has to be the final Lewis dot structure for BH3. Aluminum has 6 valence electrons in it, in the compound aluminum chloride. So same thing here. Again, you would follow the same rules for creating this compound, but you'd have to realize that in that group 13, you can only have the central atom aluminum. It's only going to have 6 valence electrons. Now there's 2 other exceptions to the octet rule, and I didn't put them in this video. Where they are is in the notes, and you should read the notes along with this video. The notes have some things that this video doesn't have. This video has most of it, but the notes have some things that the video doesn't have. You'll find those. So you'll find those other 2 exceptions to the octet rule. So there's 3 of them in all in the notes. So the idea is to watch this video, but also to read the notes as you do your assignment. All right, one last concept in this lesson is the idea of ionic versus covalent bonds. So how do we tell the difference between ionic bonds, polar covalent bonds, and covalent bonds? We've talked about these quite a bit, and we've just said that ionic bonds are bonds in which one atom passes an electron all the way over to another. The one that lost the electron becomes positively charged, the one that gained it becomes negatively charged, and they attract each other. Then we talked about covalent bonds which share electrons, but polar covalent bonds, one of the atoms is stronger than the other, and it tends to pull the electrons closer towards it. So at what point do we draw that line between a polar covalent bond, which just kind of pulls the electrons towards it, and an ionic bond in which the electron is totally passed over from one atom to another? So there's a set of numeric rules that you can follow for that. The following table gives a set of guidelines for classifying the 3 types of bonds. The classification of a bond can be determined by the electronegativity difference between the 2 elements, as shown in the table. So here's a table that will explain that. If the difference between the two atoms, the electronegativity difference, is greater than 2, that means one of the atoms is much stronger than the others at pulling in electrons. Therefore, that's going to be an ionic bond. It's going to totally take the electron away from the weaker one. If the difference between them, if you subtract the electronegativities and it's between 0.5 and 1.9, then it's pretty strong pull towards the strong guy. But the strong guy doesn't totally take the electrons away from the weaker guy. And finally, a covalent bond. If the electronegativity difference is essentially not very much at all, less than 0.4, then it's just purely a covalent bond. We don't say that even if one has a slightly stronger electronegativity, we don't say that it's really pulling the electrons towards it substantially. So that's not a polar covalent bond, that's just a regular covalent bond. So example, what type of bond does HCl, that's hydrochloric acid, form? Hydrogen has an electronegativity of 2.1 and chlorine has an electronegativity of 3.1. So the electronegativity difference is 3.1 minus 2.1 is 1.0. So according to that table up above, a 1.0 electronegativity difference would be a polar covalent bond. So that means hydrochloric acid has a polar covalent bond. Alright, so that takes care of your lesson for Monday. So again, this video is paired with the notes that you'll find in this lesson. A lot of those notes are review from the foundations unit. You can kind of skip past them if you feel like you know them, but there is some information in those notes that's not in this video, particularly about exceptions to the octet rule and a few other things. There are also some similar examples to what you saw here for how to do a Lewis dot structure of a covalent bond. So go ahead and get this done, guys. We're going to maintain a pretty rapid pace between Thanksgiving and Christmas. I'm going to have another lesson up for you on Tuesday, so get this done as quickly as you can, and I'll have solutions up for the assignment Monday night for this assignment. Okay, have a great day.